So there are three types of formulas, like we learned. There's the empirical formula, a molecular formula, and a structural formula. Now, each one gives you a different amount of information. Empirical being the least amount of information given, and structural being the most. So, empirical formula is when the subscript numbers are in the smallest whole number ratio. So that means that the numbers, the subscripts, that means the C2, the little 2's, and the small 4's, those are they can't be divisible by any number anymore. So let's say the example is C2H4, so that could be divisible by 2 still, so it's not in its empirical form, because it's in the 2 to 4 ratio. So the smallest would be 1 to 2. So the answer would be, to that answer to be in empirical form would be CH2. So molecular formula could only is exact amount. That means it can't be C2H4 is exactly ethane. CH2 is something else entirely. So in a molecular formula, that gives you the exact amount needed to make up that molecule. Such as water. Water needs exactly 2 H's and 1 O, or it's not water. So, and then you have even more information given in the structural formula. So structural formula is really just a diagram which shows you that the formula is how the formula is put together. So the example is C4H10. So C4H10, when it shows, so you would think, okay, so what is it? But when you see in different structures, that in one way, when it's laid out in one way, it's butane in the horizontal way, but when it's laid out in the more triangular type of way, as you can see from the H's, they make like a triangle. That makes methylpropane. So it shows you really that the structure truly switches the outcome. So, how do you write a formula of an element? Element, we're talking about now just regular, how it looks on the periodic table. So, when we're talking about metal and nonmetals in general, so we just write it. How does AU, which is I believe gold, how does AU on its own? It's just you write it as AU, and let's say AR, which is number 18 on the periodic table, which is argon, is also, you just write it AR, and so on and so forth. But the exception to this rule is diatomic elements. Diatomic elements are, as they exist on Earth, they exist in pairs. So, if you look at the reference table, all of group 17 falls under that category. So let's say, so F, Cl, Br, I, those all fall in the categories. Also, as well, what falls in the category is like Cl, like I mentioned, N, and O. So O, existing in the atmosphere, no oxygen, each oxygen by himself. It's actually, oxygen is paired up with another oxygen, because only with another oxygen, for example, to fill the valence electron shells. So this is all true to all these examples, that when they bond with another of its own, then it fills with a full valence shell. So how do you name and write formulas? So first we're going to talk about binary compound. So binary compound is bi, like two. So a compound made of two different elements. So that could be either Na and Cl, which is an ionic compound, a metal and a nonmetal, or a molecular compound, a nonmetal and another nonmetal, such as Cl and O. I don't even know if those come together, but that would be a molecular compound. Two nonmetals. So now we have a binary ionic compound. So binary ionic compound, that means two elements are used now in an ionic compound. So now we just know we have one nonmetal and one metal. So now we're looking at it. So how do you go from a name to a formula? So they're going to give you a name, and you have to figure out the formula. So first, the metal is the positive part of this ion, and the nonmetal is the negative ion. You really see this when you look at the reference table. What is more likely to happen? That more likely the metal will lose its electrons, thus becoming positive, and the nonmetal will more likely to gain electrons, thus becoming negative. So let's say the nonmetals, for example, chlorine, it will switch to the last three letters to IDE. So chloride. So when you write something, let's say you write sodium chloride. So it's sodium chloride, not sodium chlorine. That's how you write something. So you have to always be careful to switch the IDE. So then we have to talk about selected oxidation states. So what is a selected oxidation state? Is the number of electrons the atom is more likely to give or take. So let's say like Na, if you look in your reference table, let's say, is oxidation state, which is the topmost right corner, it says +1. So the Na, the sodium, is more likely to lose an electron and become positive by 1, so to speak, if you want to look at it that way. And then say, let's say chloride, see the topmost one is like -1, so it's more likely when we talk about oxidation states, we're actually looking for, in the non-metal, the negative one, because we know they mostly become negative, and in the metal we look for the positive one if there is any negatives in the metal, which is rare or non-existent. But we do that because all the positive oxidation states we don't worry about now, because all the positive oxidation states actually has to do with organic chemistry, which isn't in this chapter. For example, let's say sodium chloride, like I mentioned before. So sodium is Na, which is +1 in the oxidation state, and chlorine, or chloride, is -1. So what we do is we crisscross them, and we crisscross the oxidation numbers, leaving behind the positive and negatives. We don't need those anymore. So the formula is simply NaCl, and that's the end of it. So let's try another one, magnesium oxide. So magnesium, if you look at the oxidation state, is +2, and oxygen is -2. So then we crisscross, and then we get Mg2O2. So that is not correct yet, because this is ionic. So this is ionic, and this, when we talk about ionic, that ionic isn't a molecule. A molecule only happens between two non-metals. So ionic, which is what we're talking about, because magnesium is a metal and oxygen is a non-metal, has to be in the empirical form. So it has to be in empirical form. So they're both divisible by 2. So divide them by 2, and then the formula is MgO. Another example really is sodium oxide. So sodium is +1, like we said before, and oxygen is -2. So when you crisscross, you get Na2 oxygen 1, but we don't write 1s. So that would be the formula. Another example, let's say iron oxide. But iron oxide, when we look at the iron has, if you could check up, has 2 oxidation numbers. So what do you do with 2? When the metal has 2 oxidation states, the name includes the oxidation number. Now I wrote the oxidation numbers like past the iron, you see the 2 and 3. That's what it means, the name includes the oxidation state. On the test, and on the Regent, it will be referred to in Roman numerals, but I can't seem to get them. So let's say iron 2 oxide. What does that mean? So we're going to take 2. So first you take what does it mean? You take and you do both metal oxidation numbers. So let's say iron +2 and oxygen -2, that's 1, and iron +3 and oxygen -2, you use oxygen twice, that's another one. So let's say crisscross the Fe +2 and the O -2, so leave behind the positive and the negative, and now we have 2 and 2. So 2 and 2 are both divisible by 2, so now we just have plain FeO. Let's say, so that means we use the +2 oxidation number, so that one's called iron 2 oxide. But let's say we use the 3 one. So we're going to do Fe3 and O2. So we crisscross, and then we get the 2 on the Fe and 3 on the O. So then we get, the answer is Fe3 2. So that is the oxidation, that is the formula for iron 3 oxide, using this 3 from the oxidation state of iron. Now we have binary ionic compound. That means there's 2 elements in an ionic compound. So we just did from name to formula. But how about if they give you a formula? So you have to do 3 simple steps. Number 1, name the metal. Number 2, name the non-metal and add the IDE at the end. So let's say F, which is I believe which is number 9 on the reference table, which is fluorine. So you would switch fluorine to fluoride. So you have to switch it to IDE. And then third thing you should do is check the metal for multiple oxidation states. So KBr. So number 1, name the metal. K is potassium. Number 2, name the metal with IZE. Bromine becomes bromide. Great. Number 3, check the metal for multiple oxidation states. Potassium only has one oxidation state, so nothing to check for. So the name is simply potassium bromide. There's no number in between. Done. So there's the examples of, let's say, Fe2O3. So iron wood oxide. So what you do is you reverse crisscross, and when you do, the 3 goes back at the Fe, and the 2 is the O. So when you see Fe3, so when you check it up, you see that it's 3. So that means it's using the 3 and not the 2 of the iron. So the name is simply iron 3 oxide. So let's say FeO. What if there's no numbers? That means it's in empirical form. So when it's in empirical form, that means you're looking for both of the elements have an identical number, so they cross out. So when you look at O, it has -2, and you look at Fe, it has 3 and a 2. But for both of them to be the same, that means it uses the 2 because that matches to the oxygen. So which is Fe2O2. What really is, but you don't see it. So even if you would reverse crisscross, you'd still get back to the 2's. So the name is iron 2 oxide. Now we have ionic compounds that are sometimes non-binary. What does it mean non-binary? That means it has a polyatomic ion. That means that there are more than 2 elements or atoms involved in this compound. So before now we did binary, which has metal, a positive metal, and a negative non-metal, because those are the more likely of who to lose, who to win, so to speak, in the tug of war of electrons. So now there are 3 other types which are non-binary, and they all include a polyatomic ion, which means non-binary. So number 1 is when you have a positive polyatomic ion, and you have a negative non-metal. So that means that the polyatomic ion, which you could check on table E if anything is positive or negative. Next one is a positive metal and a negative polyatomic ion, and the third one is a positive polyatomic ion and a negative polyatomic ion. So 2 polyatomic ions. So here we have number 1, a positive polyatomic ion and a negative non-metal. So when we see NaCl, we see N, H, and Cl. So that is 3 elements. So now we already know there's a polyatomic ion involved. So now we look at table E and we're searching up something that matches part of this compound. So we see NH4 is a polyatomic ion, and it's found on table E. So NH4 is called ammonium, which is positive, as you could check, and chlorine, but we write chloride because a chloride is negative. So we have to do the 3 steps. Name the metal, there is no metal. Name the non-metal, it's chloride, we have to make it IBE. And then check the metal for multiple oxidation states. If there's no metal, there's nothing to check. So the name is simply ammonium chloride. Another one is positive metal and a negative polyatomic ion. So let's say Na and NO3. So Na, as you can check up, is sodium, which is a metal. So name the metal. Now the second one is name the non-metal, but there is no non-metal. There's a polyatomic ion. So, because we see there's more than 3 elements. So now we check up table E, and we see that NO3 is called nitrate, and it's negative. And so that we would do. And the third one is check the metal for multiple oxidation states. But when you check up Na, there's only 1 oxidation state, so that is plus 1. So that's done. So there's nothing more to check, so there's no number involved in this equation, so it's just simply sodium nitrate. Another example of a positive metal and a negative polyatomic ion is Fe, which is iron, and SO4, which is sulfate. Now, iron has 2 oxidation states, and sulfate has only 1. So the first step is name the metal, iron. Number 2, name the non-metal, there is no non-metal. Number 3, check for multiple oxidation states, and there are multiple oxidation states. So we know we have to be careful, and we're checking which one is used. So there is no subscript past Fe, showing Fe's charge and the charge of SO4 are the same. So you're saying, but there's a 4. That 4, SO4 is 1 unit. So you have to be very careful. The charges is past that. So pretend there was a parentheses around SO4 and then the charge. So parentheses around SO4 and then there was the 2, because then there was a 2 by the iron, and then they crossed out because it's in empirical form, FeSO4. So name is simply iron 2 sulfate because it used the 2 and not the 3 in the oxidation state. The third choice is a positive polyatomic ion and a negative polyatomic ion. So now we see NH4NO3. So now we see, of course, there's more than 2 elements. There are 4. So we look at the reference table and we see NH4 is ammonium and NO3 is nitrate. So name the metal, there is none. Name the nonmetal, there is none. Name the oxidation states for the metal, there is no metal to begin with. So the answer is simply ammonium nitrate. So how about if we have to go from a name to a formula in a non-binary compound? Okay, we just did formula to name, but how about name to formula? There's no binary, so how do I name stuff? So let's say ammonium nitrate. We're gonna do this backwards. So ammonium, as you check up in your reference table, is NH4, which has a charge of +1. And then we go up and do nitrate, which is NO3. It has a charge of -1. So we write them down, and NH4 +1 and NO3 -1. We crisscross them, and we don't write 1s, so it's just simply NH4 NO3. That is the answer. Simple. Now we have iron 3 sulfate, so there's a number, and what do you do? So when you look at it, we know iron has 2 oxidation states, +3 and -2. And sulfate, which you check on your table, is SO4 -2. So it has also -2. So what we do is, it's called iron 3 sulfate. That means we know it's using the 3 of the oxidation states. So what we do is we cross them, and the 3 goes to SO4 and the 2 goes to the Fe. So Fe2, now it's a polyatomic ion, so it has already a number past one of its letters to show that it's not like 43, which is completely different. You put parentheses around them, and you put the 3 past that to show the difference, and then that's where you put the other oxidation number. So the formula is Fe2 parentheses SO4 close the parentheses 3. Another example is, let's say, aluminum sulfate. So aluminum, when you check it up, is Al and has a charge of +3. Sulfate, which we've already have said, is SO4 and has a charge of -2. So we put them next to each other, and La +3 and SO4 is -2. So we crisscross them. So the 2 goes to the Al and the 3 goes to SO4. So formula is Al2 parentheses SO4 parentheses close 3, which is aluminum sulfate in a formula way. Now, that's the end of ionic compound naming and formula writing. Now we're talking about molecular compound naming. Now, molecular compound naming has no oxidation numbers because there are too many. When you look at your sheet, at your reference table, you will see that the oxidation numbers pertaining to the nonmetals are many. Unlike the ones that we had with the metals, which were very limited to 1 or 2. So they were workable. But in a molecular, there's too many, so we do not have any oxidation numbers. So let's say CO2. So CO2, we look up C is carbon and O is oxide. Oxide and not oxygen, because name the metal, name the nonmetal. But when we name the nonmetal, but there is no metal here, so name the nonmetal, name the other nonmetal. But we always still switch the second nonmetal, like pretend the first nonmetal is now taking the place of the metal. The second one comes later. We still switch it to IDE. So oxygen becomes oxide. So name is carbon dioxide. Now why is it di? Because there's 2. Now if you look at the chart on your right, which we'll get to in a moment, it tells you what is the names to do by pertaining the number, the subscript. So let's see another one. So CO. CO, so C we already know is carbon, O is oxide. So name is carbon monoxide. Why? Because there's only one. So there's only one number, but we don't write the one. This is how we name molecular compounds. It goes by, I believe, the Greek or Latin number system. So mon is for one, di for two, tri for three, tetra or tetra for four, pent or penta for five, hex or hexa for six, seven sept or septa, eight oct or octa, nine non or nana, and 10 dec or deca. Now, when we use, you see how all the parentheses are vowels. You only use the vowel. It really depends on the letter. After is either a vowel or a consonant. So let's say, but we look at the other examples. No, we look at the other examples that we already did, and we see that die is just not touched, so that's just die. But we look at the mon, it's just mon, because oxide already has an O, and O's a vowel, so it's not needed. We'll see this further when we look in C, carbon, Cl4. Now we name it carbon, and Cl, which is chloride, we have to switch it to IDE, but now we have to figure out the number. For 4, the number is tetra. Tetra, like 4. But why do we have an A at the end? Because C is a consonant and not a vowel, so you add an A. Now we have another one, N2O5. So let's say N, we still, even if it has a number in the first one, we also still put the Latin / Greek, whatever it is, number system. So let's say dinitrogen for the 2, and for the oxygen, we use pentoxide. We don't do pentaoxide because there's a O. O is a vowel, so we don't need pentaoxide, just pentoxide. Now we have another one, let's say N2O4. It's still again dinitrogen, and it's O4, so it's tetroxide. It's not tetraoxide, it's tetroxide, because you don't need to add the A. So that is not added. So let's say NO2, so it's just nitrogen, there's no number past the N. O2, so nitrogen dioxide. Very simple. Now we're going to begin with balancing equations with a couple of examples. But first I want to just make it clear that an easy way to spot polyatomic ions was if it ends with ATE and 8, then it's more worth it to go first look up the table E to search for the formula part than it is to first go straight into the periodic table, because you're more likely to find another giveaway, so to speak, another one easier to find. If it ends with ITE, like sulfite and chlorite, then it is more worth your while to first look at table E before you spend your time on table, I believe it's table S. A chemical equation is part of a definition of a chemical sentence. A chemical sentence is a chemical equation which describes a reaction. So it's in a sentence-like form. So let's say carbon plus oxygen yield carbon dioxide. So the carbon and oxygen in this form are the reactants. They are reacting with each other. And they yield carbon dioxide, di to oxide. So you have to understand, why isn't it equal? Because unlike in math where equal, like the 4 and the 5 equal 9, the 4 and the 5 are being replaced by the 9. But in a chemical sentence and a chemical reaction or equation, they're not being removed. They're being mushed together. So the C and the O just come together, really. And then you get CO2. So you're not replacing it. You're not replacing anything. You're not getting rid of anything. You're just yielding them together. So also to understand the law of conservation of mass. Now, what is the law of conservation of mass? It means in the chemical reaction that in the chemical reaction, the mass is neither created or destroyed. And the same thing by the law of conservation of energy, where when something happens, energy is neither gained nor lost. Energy is just rearranged. So here, mass is just rearranged, put some places, other places, but it's still equal. If you had 6 carbons to begin with, you are still having 6 carbons to end with. So here's the example of H2 plus O2 yields H2O, which is wrong because we know that H is a diatomic ion, diatomic element, and oxygen also is a diatomic element. So when you do this, there's an extra O. So what you actually have to do is 2H2, 2 hydrogens, which are common H2s, plus an oxygen 2, yields 2H2O. That only when you have 2 hydrogens and an oxygen, only then will water be created, and it won't be created singularly, it'll be created 2 at a time. Now, quantitative information is needed in a balanced equation. What is the quantitative information? Quantitative information is the coefficient, the 2's that are highlighted here, are needed to make a balanced equation. If not, it's not balanced. Now, we have examples like CH4 plus O2 yields CO2 plus H2O. Now, the first examples, the top ones, are unfinished, and they need to be done. So we're looking and we're writing this as an equation, and it needs to be balanced. That means the C's, the H's, and the O's need to add up and be exactly the same. So we look at the carbons, they match, so we'll leave them alone for now. And we see the hydrogens, they do not match. We always first look at the slash under. So hydrogen is 4, and hydrogen on the other side is 2. So they need to equal to something, and then the other oxygen is 2, and that one all together gives me 3. So I break down the oxygens to each pertaining parts. So what we think is, okay, I need to get 4 hydrogens. So when we look up at that part of the example, we see hydrogen is 2. So 2 times what equals 4? 2 times 2. So I put a 2 before the H2O, and that gives me 4. But the 2 doesn't only affect the hydrogen, it also affects the oxygen. And that oxygen is the one with the 1. It's only one oxygen in that part. So 1 times 2 equals 2. So we add it, we cross out the 1 over by the oxygen, and we make it into a 2. So now at this side of the oxygen information, we now have 4 oxygens, because we add the first 2 and the second 2. Now we have 4. But on the other side, we still only have 2. So what we do, we have O2. 2 times what equals 4. We do that again, and 2 times 2 equals 4. Now when you look at the completed formula at the bottom, we see CH4 is in touch, and then we see 2O2, the coefficient is 2, and we also switch the coefficient before the H2O, because when it's multiplied, they equal each other. This is a balanced equation. Now let's do another one. C3H8 plus O2 yields CO2 plus H2O. So we count out how many carbons, how many hydrogens, how many oxygens, and we do this for both sides. The parentheses, when used, means that that's a total at the moment of start, but then I break them up so it's easier to multiply. So then we look at carbon 3, and the other carbon is 1. So what times what equals 3? So 1 times 3 equals 3. So I have to put a 3 before the carbon on that side of the equation. So great, that switches my carbon, but it also switches my oxygen because that's connected. So 3 times 2 is 6, as you can see. So now so far I have 7 on my side, but we're not done. Now, we could switch the O now, the other oxygen on the other side now, to match that one, but it's very confusing. So what we're going to do is now to the hydrogen, because the hydrogen also affects the oxygen, so why would you count that twice? So now you go to the hydrogen, and you see on that side, on the left side, we have 8 hydrogens, and on my right side, I only have 2 at the moment. So 2 times what equals 8? 2 times 4. So I put a 4 before H2O, and now I have 4 times 2 is 8, so now my hydrogens are equal. But the 4 also affects my oxygen. So 4 times 1, because there's only 1 oxygen on that side, equals 4. So now I add my oxygens together, and I get 6 plus 4 is 10. So now I have 10 oxygens on that side, on the right side. Okay, and I have 10 on that side, but I still only have 2 oxygens on my left side. So 2 times what equals 10? 2 times 5. So on the left side you put the coefficient of 5. So now when you look at the balance equation at the bottom, see 5 times 2 is 10. So that equals out our oxygens. 3 times C equals out our carbons. Times 6 gives me 6 oxygens. And then 4 times O gives me another 4 oxygens equals 10, matches my other one. And 4 times 2, the H's, gives me 8, which matches the other one. Now we're going to go into another example, and I'm really sorry that my pointer I really don't understand and know how to do yet, how to put in a pointer into the slideshow, but we're going to do this as best as possible. So the first example is CaOH2 plus HCl yields CaCl2 plus H2O. So in a balancing equation, we need everything to be balanced. So we look at the Ca's, they're balanced. The O's aren't balanced at the moment. The H's aren't balanced either. The original numbers are the ones under the blue stripes. So we need to have equal H's and equal O's. So let's go to the H and the O's, which are together. They'll be affected as one. So I need 2 O's. Okay, so I put a 2 before H2O, and now I have 2 O's. But the 2 that I put before H2O also affected the H. So H2 times 2. So 2 times 2 is 4. Now there are 4 H's on the right side. But now there's 4 on that side. I need also 4 on the left side, but there's only 3. So I go and I ate to HCl, and I put 2 before HCl, thus making me have 4 H's. But it also affected Cl, which before had 1, and now has 2, thus equating it to the other Cl, which is on the other side, making everything equal. So the final balanced equation is CaOH2 plus 2HCl yields CaCl2 plus 2H2O. Another example is NaNO3 plus CaCl yields NaCl plus CaNO3 2. So in the beginning, Na starts with 1, NO3 starts with 1, Ca with 1, Cl with 2. And on the right side, it starts with Na1, NO3 2, Ca1, and Cl1. So the only thing that isn't changed overall is the Ca's, those are equal. So we need equal NO3s. So I have two NO3s on the right side. I need 2 on the left side. So I put a 2 before NaNO3. So that gives me equal NO3s, but that also affected my Na. So now I have 2 Nas, and now I have to switch on my right side also my Nas to match the new current status. So I put a 2 before NaCl, thus switching my Na now to be again equal to the other Na, making it 2. But also affected my Cl, which at the bottom 1 times 2 is 2, and that also equates it to the other Cl, which are on the other side. So the total and complete example equation correct is 2NaNO3 plus CaCl yields 2NaCl plus CaNO3 2. Now there's another example of Fe plus O2 yields Fe2O3. So on the left side we start off with Fe is 1 and O is 2. On the right side Fe is 2 and O is 3. So nothing is equal. So something has to be changed. Everything has to be changed. So let's go to Fe2O3. Those are together, and that is actually synthesis. Just saying. But okay, so we're gonna do that first if they're together, and they're gonna be corresponding to the other side. So what you do is you're gonna times Fe times 2, and you got 4. And then so now I have times Fe2O3 times 2 everything. So now I have Fe on the right side equals 4 and the O equals 6. So now I go to the left side and I very simply put a 4 before Fe. That's giving me 4 Fe's like the right side. And I put a 3 before O2, give me 6 O's just like the right side. So the total example when it's balanced is 4 Fe plus 3 O2 yields 2 Fe2O3. Another example, but this is, and you can really use this in the other examples as well. This example we're going to do twice, explain 2 ways, method 1 and method 2. The first method is the one that we have just done multiple times, is shown right here. So let's do C C8H18 plus O2 yields CO2 plus H2O. So as we already know, the first layer is uncompleted. So now we have 8 carbons, 18 hydrogens, 2 oxygens. We start off. Next one, we start off with 1 carbon, 2 hydrogens, and a subtotal of 3 oxygens. Great. So now we go on. Now, easiest, let's start with the carbon because it's first. So, what times 1 equals 8? So, 1 times 8 equals 8. So now I times the CO2 times 8. So also affects my O. So 2 times 8 is 16. So I separate the O's to make it easier. And 2 times 8 is 16. So now I have 16. Great. Now I still need my H's to be even. So 2 times what equals 18. So 2 times 9 equals 18. So I put a 9 before H2. So, and that gets me 18. So now I have 8 and the 18s are equal. My oxygens aren't equal now because my 9 times O is 9. So now I have 16 plus 9 is 25. So now 25, and I have 2 oxygens on the other side. So it's really not matching. Now the lowest common multiple is 50. So 2 times 25 is actually 50. So what times 25 equals 50? Times 2. So what you do is you can't put a 2 because you already put constants before everything else. You already put an 8. You already put a 9. So what you do is you double everything. So now what you do is you do 16 CO2 plus 18 H2O. You double everything, and you go to the other side. So 2 times 25 equals 50. So you just put a 25 before the O2, and that is just done. Now, when you look at the other side, that is the first method that we did in the other examples. The second method is C8H18 plus O2 yields CO2 plus H2O like we did before. So we simply do figure out the carbons times 8, figure out the hydrogens times 9, and you do 16 to 9, and then you get O is 25. So altogether 25. So what you do now is everything is equal except 1. So what you do is you look at the bottom and it's 25 over something. I couldn't put a 2 there. I didn't figure out how to do fractions, but it's over 2. What you have to do, what you simply know is that everything times 2 will get you 25 divided by 2 is 12.5. So you can't have a decimal. But you know, if I could do half, then I'll be done. But 25 divided by 2 is and if you times everything by 2, it'll be equal. So now what you do is you just times everything by 2, and then you get 2 C8H18, 25 O2, 16 CO2, plus 18 H2O. If you don't like this method and you do not understand it, you do not have to use it. The first method is perfectly fine. There are 4 different types of reactions: synthesis, decomposition, single replacement, and double replacement. Now, synthesis is when you think about photosynthesis, is putting food together. So it's put together. So A plus B yields C. When I put 2 H2Os and an O2, I will get water. I'm putting it together to get a different thing. Decomposition is when we think about something decomposing. It has a full mass and then it's breaking into 2 different parts. So C yields A plus B. So I take 2 H2Os. When I take two molecules of water and I break them apart, I will get 2 H2Os and an O2. That's what happens when I break it apart. Now, single replacement and double replacement are generally the exact same thing, but a little different. So in single replacement, there is one element alone and a compound. So A plus B, C yields AC plus B. So keep in mind, think about A is first, B is first, and C is second, first in the things. So A replaces with A, and B has nothing to replace with, so it just stays there. So A replaces with B, so it becomes AC, and the B is moved to the side, so it's AC plus B. So we see this in the example, Zn plus 2HCl yields ZnCl2 plus H2. That means Zn is 1, 2H is 1, and Cl is 2. So Zn takes the spot of 2H. So now I get ZnCl2. It's Cl2 because there's a 2 before the H and the Cl. That means there's 2 H's and 2 Cl's. So Zn takes the place of the other first, and Cl2 plus H2 because that one has to be moved. Now, double replacement is when the first replaces with the first and the second replaces with the second. In a reaction, everything switches partners. That means AB plus CB yields AD plus CB. So A is first, B is second. C is first, D is second. So A and C will change places, and B and D will change places. So you see how it becomes, now we're going to keep it in the order of whoever came first will go first. So it won't be CB, AD. It will be AD, CB. So A takes D and B takes C. But it's more like A takes D because that's first. Now B takes and C, which is the first and the second one, takes B. So A is first, and it replaces C. So it takes A, D. Now C is first in the second one, and it replaces A in the AB, so it becomes CB. Example is KNO3, which NO3 is a polyatomic ion, plus NaCl. So K is first, NO3 is second. Na is first, and Cl is second. So K will take the place of Na, so it's KCl. And Na, which is first and second one, will take the place to the NO3, so it's NaNO3, which is the answer. They're double replacing each other. Now, forming and breaking bonds are very simple. When a bond is broken, energy is absorbed. Now, when something is absorbed, it's called endothermic. When a bond is created, energy is released, and that is called exothermic. Think about it like exit, released. So table I will actually show you if you check up table I. At the moment, we're not using most of table I in this chapter, but when you see table I, it's going to tell you under the category of delta H, you see it says negative numbers, and then the number, or positive, then the number, and they're next to reactions. And you look at the bottom, and it says a little asterisk. The delta H values are based on molar quantities, which we aren't talking about, represented in the equations. We're not talking about that part yet. We're talking about a minus sign indicates an exothermic reaction. So table I will tell you if certain equations are overall more exothermic. So that means that overall more bonds are being created than are being broken. So let's say to create H2, so let's say here's an example of to make CO2, to make carbon dioxide. So you have carbon and oxygen yields carbon dioxide. So that is overall exothermic. That means more energy is being released because more bonds are being created. Because to bond the C and the O's together, there are more bonds than there is needed to be broken, because that's how it is overall. So it isn't talking about, because every example has exothermic and endothermic, has both. But overall, which one stands out most? That is what it's talking about. In which, and how do you differentiate them if it's exothermic or endothermic? Which is overall more? So you just know like 3 facts. Every chemical reaction requires bonds being broken and bonds being created. Always, number 2, always breaking is endothermic, and always forming is exothermic. And number 3, some reactions are more endothermic and some are more exothermic. Just really facts. That's what will happen. There will be more breaking or more bonding. That is what just happens. And that's it. That is the end of the chapter. And just a simple saying, burn and explode are just words describing energy release. But the difference between burn and explode is the difference in the rate it's happening. Like burn, you could see something burning, But exploding, it's in a millisecond or something, and it's a lot faster. And that is the only difference. And that is the end to chapter 5.